So, hi, I'm Craig Duguid, and I'm a postdoc at Newcastle University. And I'm going to talk a bit about my PhD work that I did at Leeds University as part of the CDT in fluid dynamics, under supervision of Adrian Barker and Chris Jones. So to kind of motivate one of the applications of the work was, so this is a plot of all confirmed exoplanets as of sometime in the middle of summer last year, plotted as their orbital period along the bottom and their mass in days and their mass in Jupiter masses in the vertical, and colored by the eccentricity of the orbit. And the particular planets that are of interest, or one of the applications, is these planets up here, which are called the hot Jupiters. So these are massive planets, like a tenth or more of the mass of Jupiter, and they're on short period orbits, 10 days or less, which means they're very close to their host star, like within the orbit of Mercury, for example. So these planets, much like the Earth-Moon system, where the moon raises tides on the Earth, and then the consequence of this is that the moon is migrating outwards from the Earth, these planets are expected to excite tidal flows within their host star and then consequently have migration. And we have observations of this in a particular case of WASP-12b, which we've observed over the past 10 years to be migrating in towards its host star. So a little bit more about this mechanism. Essentially, you'd have this planet orbiting around its host star, and the gravitational potential of this planet acts to deform its host star and excite a tidal flow, which causes this deformation in the star. Dissipation in the system then acts to misalign this deformation with the line of centers, and it also modifies the gravitational potential of the star. And then this feeds back onto the planet, which then evolves its orbit. So if there was no dissipation in the system, then this deformation would align with the line of centers, and then due to the symmetry, there would be no evolution in the system. So a key thing in this interaction is the dissipation of the tidal flow. So classically, the dominant mechanism, or what's thought to have been the dominant mechanism for tidal dissipation, is the interaction between the large-scale tidal flow and the turbulent convection within the convective region of the host star. But it's been recognized that when the tidal frequency, so the frequency of the orbit of the planet, is larger than the convective frequency, then the efficiency of this mechanism to dissipate the tidal flow would actually be reduced, so it would be less efficient. But how strong that efficiency should be reduced has kind of been a debate. So I'll kind of go through the theoretical grounds for this. So all of this comes from what's called mixing length theory. So we say that this effective viscosity or turbulent viscosity is proportional to some mixing length velocity times some length scale. So this would be our convective velocity, and the length scale is our convective length scale, which is how far the eddy travels before it dissipates and releases its energy into the background. So Zahn recognized that actually the eddy will not be able to travel this full distance if the tidal frequency is large, because the tide would have changed direction. So instead, he proposed that you change this length scale to be the distance that the eddy can travel in one tidal period. So that happened. So he did that work in the 60s. So about 10 or 11 years later, Goldreich and Nicholson came along and said, well, we need to actually care that this convective region is turbulent. So we have to consider the consequence of having a Kolmogorov-like cascade there. So they proposed that they should consider only eddies that have timescales that are comparable with the tidal timescale, and then take the length scale from those eddies and use that in the mixing length. So the consequences of these two predictions are that in the low frequency regime, so when the tidal frequency is less than the convective frequency, in both cases, you should recover the standard mixing length prediction. But in the high frequency regime, when the tidal frequency is larger than the convective frequency, then the effective viscosity should scale for Zahn as 1 over the tidal frequency, and for Goldreich and Nicholson, 1 over the tidal frequency squared. So a kind of obvious question here is then, well, it doesn't seem like a big deal. It's just an argument about what this length scale is. And the consequence seems to be just the power here is either a 1 or a 2. So if we do like a back of the envelope calculation and we consider a Jupiter mass planet on a 1-day orbit around a sun-like star, which is analogous to WASP-12b, and we do a quick calculation on how long it would take for that planet to migrate into its host star, given these different prescriptions, then the mixing length prediction is considerably quicker than the other ones. So this is actually very quick on astronomical timescales. And in the Goldreich and Nicholson case, if this is the one that's true, then this is actually a timescale that's longer than what the lifetime of the system will be. So essentially what it's saying is that in the fast tides regime, when the tidal frequency is larger than the convective frequency, then it would be saying that this mechanism is not efficient at dissipating the tides, and we would have to think about other mechanisms, of which there are plenty. So our approach was to consider a small patch of the convective region of the host star. The reason for looking at a patch is because global models are very expensive, and this problem, in order to probe low frequencies, you need to be able to resolve both the timescale of the convection, but also the timescale of the tide. So if the tide has a low frequency, it's got a long period, so you have to resolve long timescales as well. So within this patch, we model the standard Rayleigh-Benard convection under the Boussinesq approximation, and therefore we're incompressible. And we decompose the velocity field in terms of this U, which is all the convective motion, and this U naught, which is our tidal flow. So that's this down here. So instead of applying a force, a body force that would be our tidal forcing, we instead can do a little bit of analytical work to find out what a tidal flow would look like from a resulting tidal forcing. And so this is a tidal-like flow. It's not quite exactly there, but it's close. So in this work, we did an extensive kind of search of parameter suite. So the most important parameter that we looked at was this tidal frequency here, this omega, because of course we care about the frequency, the tidal frequency dependence of the effective viscosity. So some of the other things we looked at were this amplitude dependence. So what this would be analogous to the mass of the planet. We also cared about the Rayleigh number. So this is the strength of convection. So what this also tells you is if the Rayleigh number is higher, the flow is more turbulent. And if you've got a low Rayleigh number, then we could be in the laminar regime. This is important because the Goldreich and Nicholson prediction assumes a Kolmogorov-like cascade. We did a brief look at the Prandtl number. Oh yeah, another thing with the Rayleigh number is the Rayleigh number controls the convective frequency, which is where the transition between the low frequency regime that should agree with mixing length theory and the high frequency regime, which should be either Zahn or Goldreich and Nicholson or something else. The other thing we explored was changing the size of the domain. So of course our main simulations were with a domain that's large enough that if you pick a larger domain, the results are independent of increasing the domain size. But one thing that we did was we actually reduced the domain size to constrain the problem to be able to compare to some asymptotic analysis. Okay, so there's not enough time to pick into the details of kind of how we got to the results, but I'm just going to kind of rattle off the kind of main results. So obviously the thing that we were mostly concerned with was the frequency dependence of the effective viscosity. So we did actually recover this frequency independent regime at very low frequencies, but much lower than the convective frequency, where we would expect it to transition to that regime. But we found this kind of low frequency regime that's below the convective frequency that has this power law of minus 0.5. So this is brand new. This was not predicted by any theory or observed in any observations before this. So that has some interesting consequences. We also found agreement in the high frequency regime with Goldreich and Nicholson of obtaining this minus 2 power law. And like I say, in the constrained domains, when we had small domains, we were able to constrain the convective flow, and we were able to use some asymptotic analysis that would be able to predict this minus 2. A really intriguing thing that came out of this was the possibility of negative effective viscosity. So this is anti-dissipation, or what Jim Fuller has called inverse tides. So the consequence of this would be that the tidal migration would evolve in the opposite direction. So instead of the hot Jupiter migrating in, it would migrate out or excite eccentricity. So in looking into this, of course, we find agreement with Goldreich and Nicholson, but they also have assumptions in their model. So we wanted to test them. So we care about looking at the spatial structure. So one thing we were looking at was the classic wave number spectrum of the kinetic energy to see whether certain Rayleigh numbers were Kolmogorov-like or not, whether we had that Kolmogorov cascade or not, and also what scales contribute the most to the effective viscosity. So the consequence of looking at this was we actually found that we don't really require a Kolmogorov cascade to get the -2 power law in the high frequency regime. So although we have the agreement in the power law of Goldreich and Nicholson, their assumption, that assumption is not required to obtain it, at least in our model. And we also found, so they predicted that the resonant scales would be the ones that dominate, but in fact, we find that the largest scales always are the dominant contributions to the effective viscosity. So another thing we cared about was the temporal behavior. So we looked into the frequency spectrum. So it's the temporal spectrum of the quantities such as the volume average kinetic energy or the volume average Reynolds stress. So this can be thought of as taking the Fourier transform of a time series of some quantity. And we observed this robust -0.5 power law in the frequency spectrum. And it turns out that -0.5 power law in the frequency spectrum of the kinetic energy, the range of frequencies that it covers matches the same range of frequencies as the -0.5 power law in the trend in the effective viscosity. So what this is essentially saying is there could be a relationship between the frequency spectrum of the kinetic energy or the Reynolds stress and the trend in the effective viscosity. I should importantly say that this is only true in the low frequency regime, and in the high frequency regime, the effective viscosity no longer follows the frequency spectrum. But we have the asymptotic analysis to hopefully explain some of that. Another kind of key and important result that came out of this is if we pick a large enough box so that we're box size independent, and then we apply appropriate scalings to the effective viscosity and the tidal shear frequency, then we can collapse the effective viscosity trend onto a single master curve that is Rayleigh number independent. So this is quite an important result because this can then be used to parameterize the dissipation from this mechanism. And in fact, this has been done by Adrian Barker in his 2020 paper. Another small aside out of this is actually in the very low frequency regime, when we become frequency independent and we should agree with mixing length theory, although this is kind of crude, the results are suggestive at least that standard mixing length theory is under predicting the amount of dissipation in the low frequency regimes. So I've skipped over a lot of the details. If you're interested, you can have a look at our papers or my thesis, which is now on White Rose. So kind of the main takeaways here are the ones in orange. So I'll kind of quickly go over them. Like I kind of just said, it looks like in the very low frequency regime, the mixing length theory underpredicts the amount of dissipation from this mechanism. We also observe this kind of intermediate regime, which has got this new -0.5 power law that had not been observed or predicted before. And it seems to be related to the frequency spectrum of the convection. We also find agreement with the Goldreich and Nicholson power law, but we do not really find that their assumptions that they take to obtain that power law are required. So that's quite interesting and suggests that there's more work to be done to understand this. And also this anti-dissipation is a very interesting thing to have came out of this as well. And finally, we have this, with appropriate scaling, we have this master curve that we can collapse the results down to that can be used in parameterized models. Yeah, so that's everything. So thank you for listening.